Okay, today from the lift bridge at Canal Park, we're going to wander down to the Rose Garden and just sit here for a minute and go over what we've learned, because from here on out we're going to need to know the C++ statements, and so we should have a pretty good idea as to what they are and how they work. Okay, today let's do a quick review of the C++ statements that we need to know for the first couple weeks of the semester. We will use these all semester long, and they show up in Project 1 and Project 2, so we should be familiar with how they work. There are three things we need to know in our first couple of programs. That is how to create variables. We say we declare variables. Remember, a variable is what you store data in. Okay, so how do we create variables? How do we get data into them? And how do we display the results? So let's take these one at a time. How do we declare variables? You can't use a variable. You can't use anything that hasn't been declared. So the first thing we do in every program we write is we tell the computer what things it has to keep track of, and that's called declaring our variables. In the first two yellow lines you see here, we've got some variable declarations. These come from your textbook, from your author, who has an example of a program where you enter how many candy bars there are in a package, and you enter the weight of one candy bar, and then it calculates what the total weight is of the whole package. Okay, so the line that says int number of bars is a variable declaration. It creates a single place to store data called number of bars, and it sets that place up so that it stores an integer. You got one candy bar, or two, or three, or four, or six, whatever. The second line, double, one weight and total weight, declares two variables. One weight is the weight of one candy bar, and total weight is the total weight of all of them. We're going to need all of those items of data to solve this problem. One weight and total weight have been declared to be doubles, which means they store real numbers. So the weight of a single candy bar might be 2.4 ounces. Now, your author does something kind of strange in the examples from the textbook. Your author loves to use long variable names so you know exactly what's being stored. Number of bars is the number of candy bars in the package. We can't leave those little underscores out. You can't put spaces between words, because the compiler will think that you've got three different variables you're trying to declare, and there'll be error messages. So every variable name has to be one continuous group of characters, and if you've got more than one word in it, you could use underscores for that. I actually think this is a bad thing to do, because in a program you might have to type all kinds of commands to declare your variables, read data into them, process the data, and then print out the results. You might have to type these variable names over and over and over and over and over and over and over again, and you don't want long names like this. Maybe a better thing to have done would have been to make them shorter. Number of bars could be shortened to number. One weight could be shortened to weight. Total weight could be shortened to total. And that's usually the way it goes. But you see lots of long variable names in your textbook because your author wants to make sure you don't get lost and can figure out what's being stored. Just remember, though, it's not the best programming style to make long names like this. Okay, so what's stored here? Number of bars is an integer. So an integer is a positive or negative whole number, or zero, and it stores the number of candy bars. One weight and total weight are doubles, meaning that they can store data that has a fractional component, okay, 1.34, or something like that. Now that we've got variables created, how do we get data into them? And the way you get data in, usually is with an assignment statement. An assignment statement will say, take a number and put it into this location in memory. Now we can look at the first yellow line at the top. Total weight equals 1 weight times number of bars. All right, that makes sense. If the weight of a candy bar is 2.4 ounces and the number of bars is 6, then you multiply those together and you'll get the total weight. In orange, I've got the assignment operator here. You can see that. It looks like an equal sign. But don't think of that as meaning equals. Think of that as being assigned to. It takes whatever number is calculated on the right and it puts it into a location on the left. So once we've done the math and done the calculations and figured out the total weight of all the bars, then that number gets sent over to total weight, which is on the left. So this works from the right to the left. Assignment operators have to have one thing on the left. You can't flip these around. It doesn't make any sense for the computer. So it figures out what's going on the right, comes up with a number, and then it stores it in the location on the left. Down below, you can see some of the ways this happens. You could put the number 21 into age. You could put your cost, whatever that is, into the variable my cost with an assignment statement. You could take the diameter and multiply it times 3.14159 and put that result into circumference. We're always figuring out what's going on the right and then taking that final answer and moving it over, copying it into the location on the left. So assignment statements are important. I mentioned that you can't read these as being equal to, and here's a good example of that. This is perfectly valid C++. Number of bars equals number of bars plus 3. But it doesn't make any sense algebraically. How can something be equal to itself plus 3? But the way this is working is, first we focus on what's happening on the right-hand side. Number of bars, let's say it is a variable containing the number 6. Okay, so take 6, add 3 to it, now you get 9. Take the number 9 and then assign it over to number of bars. Number of bars was 6, and now it's been replaced by 9. So this thing works from the right to the left. We'll always have to be careful about the way we read assignment statements. For sure, make absolute sure that you only have one thing on the left-hand side, and that's the location that data is being put into. Now, when you use assignment statements to put data into a variable, like we see here, we have a variable called mpg, miles per gallon maybe. It's a double, so it stores real numbers. The line below it initializes the variable. Initialization is what we call the statement that assigns data to a variable for the first time in a program. So we're initializing miles per gallon to be 26.3. We're putting that in there. And there are many ways to do this. Down at the bottom of the slide you see method 1 and method 2. Method 1 uses assignment statements to get data into miles per gallon and area. Method 2 puts the assignment data in parentheses. We'll talk about that toward the end of the semester. From the beginning of the semester, we won't use that very much. We'll use assignment statements because they just make a lot of sense. So we can assign data to a variable. What's another way to get data in? We could read it in, have the user type it. And this usually requires 2 steps. A prompt, where we say something like, enter your age, and the user reads that, and then they respond by typing something at the keyboard, and whatever they type, we read it in. So a cin statement is a way of getting data into your variable. The way it works is that it takes data coming from the keyboard through a file stream that we call the cin, the input file stream, and that data flows right into age. The little greater than signs that you see there kind of indicate the direction of the flow. From cin, they're moving into the variable age. We have a name for that, those two greater than signs right next to each other. We call that the extraction operator. We are extracting, or we're pulling something out of the stream so we can use it. And if you look at the statement above, the cout statement, you can see that here we've got an operator that has two less than signs right next to each other. Again, they're kind of pointing the direction that things go. Enter your age is going to be printed as output onto the screen. So that's going to be inserted into the stream and it's going to flow out to the display. And that operator, those two less than signs, is called the insertion operator. If you were going to read in three different numbers to three different variables, you could do that relatively easily. We can have multiple data items come in, just put spaces between them. So here a cin statement is going to extract from the file stream the first three things it finds. So 34 will flow in and go into V1, 45 will flow in and be put into V2, and 12 will flow in and be put into V3. The data is on the bottom there, that's what the user would enter, and the cin statement would read it in. Now let's talk about output for just a second. We've talked about this a little bit when I mentioned the cout statement at the top that said enter your age. That was a prompt. You'll notice that we didn't try to go to a new line after we printed that. We went right to the next statement that read in the age. That makes sense because then it all happens for the user on one line. It says enter your age, it stays right there, the user types in a number, hits the enter key, and it's a done deal. That's usually the way we want it. Once you've got data in, it's also a good idea then to just check it and make sure you got what you think you did. And we can do that pretty easily using something called an echo print. At the bottom of this slide, you see that. The cout statement sends three things out to the display. It sends age, not the word age. Okay, age is a variable. It sends out whatever is contained in that variable. So let's say 20. Okay, it sends that number out. Then it sends out a string of characters, and now we see the double quotes. Was entered. Okay, that exact stream of characters goes out. And then the end line constant, ENDL, is also sent, and that means go to a new line. So this cout statement would say 20 was entered, and then go to the next line. Now, so far we've talked about data, how to declare variables, how to get data in, how to print results out. I have a few more things to say about data before we move on, because this will be important for what we do this week. We've established the fact that there are integers and doubles, that int stands for integer and double stands for real numbers. You have to be careful in this class when you type something. If you type something like 2, that's an integer. If you type 2.0, that's a real number. Now the slide here says they're not the same number. They are, it's the number 2. But they're represented in different ways. Without a decimal point, you always have integer data. With a decimal point, 2.0 is always represented as a real number. And those are two different data types, integers and real numbers. The way they're stored in the machine is not the same. And so we have to be very careful about this. Integers get stored as exact discrete values, but real numbers have to be rounded at some point because we only have so much storage space to represent them. Here's a table that comes from your textbook that shows all the various data types that store numbers, and you can see on the column on the far left-hand side where it says type name, short, int, long, float, double, long, double. Okay, those are all different ways of storing data. There are really only two that we will actually use in here, and I put a little red box around both of them. Int for integers and double for real numbers. let's start with int. A standard integer takes up 4 bytes. Now a byte is 8 bits, so that's 32 bits. And in that many bits, you can store a number as small as negative, oh, what the heck is this? 2,147,483,647, all the way up to 2,147,483,647. That's the range. You can't store numbers that are larger than that or smaller than that in an integer. So for most science and engineering applications, we're going to want more precision than that and a broader range. And so we might want to use real numbers. If you go down to the line that represents doubles, you can see doubles are stored in twice as many bytes. That's why they're called a double. They're twice as big. Instead of 4 bytes, they're stored in 8. They're stored in a very different way than integers normally are, and it allows us to have a huge representational capacity, approximately going from 10 to the negative 308th up to 10 to the 308th. It's a gigantic range. So we love to store data in doubles if we can. They're not appropriate for everything. An integer variable is appropriate for things that have discrete values. So, how many brothers and sisters do you have? Well, I've got 3. Okay, you don't have 3.4 or 2.196 or anything. It would actually be an error to make the number of brothers and sisters you have a double, because it could introduce a whole range of values that are inappropriate by accident. If we make an integer, we know we can only get 2 or 3 or 4, but we can't possibly get, by mistake, 2.37 or anything else. So some data should be integers, and some data should be doubles, and we use the 2 of them. There is a data type that's not a number, and that's character data. The char data type stands for a single character. So at the bottom of the screen, you see I've declared a variable called letter, and it can store a character. And here I'm going to put a character in. I'm going to put the character A, the lowercase a, in there. Now here you do have to watch it a little bit. If you're just dealing with a single letter, you put single quotes around it. If you are dealing with a string of characters, that might be like a person's name or something else, you put double quotes around it. The char data type only takes single letters, so make sure you put just a single quotes around it. There are lots of examples from your textbook that talk about this and entering multiple items of data. You can take a look at this slide in more detail if you'd like, but in the interest of time, I'm going to move on to the string data type, which is the one you might use most often. Strings are collections of characters. And so you see at the bottom I've declared a string variable called name, and I put into it a gigantic long name, all in double quotes, because character strings always are in double quotes, and the whole thing goes in and gets stored in that variable. So this isn't one character or 2, this is a whole bunch of different characters. On some compilers you have to include the string header file. That include statement needs to go up near the top in order to get a library of routines that let you process strings. Strings didn't come with the language originally. They're not what we call a primitive type. So you may have to include the string library for that. And then finally, let's get back to numeric data and try to tie this together into character data. On the left-hand side, you see the numbers from 0 to 15 in base 10. In the center, you see their binary representation. So 0 is 4 zeros. A 1 is 0, 0, 0, and one group of 1. A 2 is 0, 0, one group of 2, and then no groups of 1, and so on. All of the values from 0 to 16 can be represented in 4 bits. And we've got those 4 bits there. This is important because what we have to realize is, even though we think of the computers as handling things like strings, names, characters, all they really only handle numbers. And so, from this chart, what you can see is that every single character you type at a keyboard has to be turned into a number in order to be stored. I put a red box around one of them here, the character A, a capital A. And if you look, that's on the right-hand side of my box. If you look to the left-hand side of my box, you'll see that that is stored as the number 65 in the computer. And a capital B is stored as the number 66, and so on. It has to be that way because we have to use binary digits, zeros and ones, to store things. And every time we do that, we're making a number. We'll use this slide later in the week when we do an exercise that comes up. This is called the ASCII table, the American Standard Code for Information Interchange. This is the way to decode all the data that might go into a machine, into a computer. I'll never ask you really about what ASCII stands for, but I think you should be aware of the fact that when you type a term paper or a document in Word or Google Docs or whatever, you're typing in all kinds of words at the keyboard, but every single character you type is being turned into a number. Whether it's uppercase A or lowercase a, whether it's a space or a digit. Notice even the digits 0 through 9 are turned into the values 48 through 57. It's not what you'd expect from this kind of a conversion process. But we'll get real familiar with this later in the week. I thought I'd show it to you now, and there we go. So that's our review for today. Make sure you know how each of these statements works. If you have questions, please join the discussions on that or send us an email. We'd be glad to work that out with you. So, very good. Thanks for watching.